Hi everyone. Today our group will present our project title Precision in Process, which focus on developing a low cost, high accuracy temperature monitoring system for industrial application. Many industries require continuous temperature monitoring to ensure product quality, improve safety, and reduce operational costs. Our project aims to provide an affordable solution that is accurate, reliable, and suitable for real-time monitoring. Before explaining our solution, let's first understand the problem. Industrial temperature variation can cause serious financial losses and safety risks. For example, in food manufacturing, incorrect temperature can spoil products. In chemical processing, unstable temperature may affect product quality or even create dangerous situations. HVAC power and power generation system also require precise temperature control for efficient production. However, many existing monitoring systems are not making them difficult for small industries to adopt. To solve this problem, we developed a system using the LM35 precision temperature sensor together with the Arduino Mega. The LM35 was selected because it provides high accuracy, require very little calibration, and give a direct Celsius output. Combined with the Arduino, it creates a simple and efficient system to monitoring temperature continuously in real operation. We compared several temperature sensors before selecting the LM35. Compared to the HT11, the LM35 measure temperature much more accurately and respond faster. Compared to PT100 RTD sensor, the LM35 is much cheaper, easier to connect, and does not require complicated signal conditioning circuit. Overall, the LM35 offer the best balance between accuracy, simplicity for our project.
Now let's look at the actual core mechanism of the system. This slide maps out the clear four-stage pipeline we designed to translate raw physical thermal energy into actionable digital data. First, the input. We began with the physical environment, capturing the ambient environment temperature. Second, the sensing stage. For this, we utilized the LM35 sensor. It converts the physical heat into an analog voltage. The crucial detail here is the scale factor. It delivers exactly 10 millivoltage per degree, providing a highly predictable linear output. Third, the processing stage. The analog signal is fed into our Arduino using its built-in uh, 10-bit analog to digital converter. It translates the 0 to 5 volt analog readings into precise digital increments ranging from 0 to 1023. Finally, we have the output. The process data is pushed into a real-time 16 by 2 I2C LCD screen and the serial monitor, giving us an instant readable environmental status. Moving forward, before buying components or melting solder, we needed to validate our processing code and electrical logic. We did this entirely in a simulated environment using Thinkercad. However, we had a platform limitation. Thinkercad doesn't natively support a dynamic LM35 temperature model. Well, to overcome this, our strategy was to use a soil moisture sensor as a unique proxy to feed varying analog voltage into our system. This allowed us to fully stress test how the code handles dynamic environmental fluctuations. The outcome was a complete success. We validated our signal processing algorithms and caught potential wiring or logic errors early, saving us critical time and budget before moving into physical assembly. On slide 7, you can see the actual physical assembly for our prototype. We translated our circuit layout onto a breadboard with three core pillars. First, the nerve ending, the physical LM35 sensor actively detecting ambient fluctuations right on the breadboard. Second, the brain, the Arduino Mega 2560 running our real-time algorithms, reading those tiny voltages and converting them into actual temperature readings or values. The third, the dashboard, a 16 by 2 I2C LCD display. Crucially, as you can see in the inset photo, once programmed, the system operates completely standalone. It updates continuously and reliably without needing a constant tether to a computer. This proved our system isn't just a theoretical concept; it's fully functional, highly responsive, and a standalone tool.
Okay, Assalamualaikum. My name is Muhammad Azri bin Sukupi. My message number is DD240035. Okay, today I would like to present to you about the LM35 sensor calibration hysteresis curve. Okay, this slide present the calibration hysteresis curve of LM35 temperature sensor. The purpose of this test was to compare the LM35 reading with the reference thermometer during the both heating and cooling process. As shown in the graph, both LM35 sensor and the reference thermometer follow a very similar trend through experiment. This indicate that the sensor has a good linearity and is able to accurately track change in temperature. The maximum measurement error recorded was only 0.3 degrees Celsius, which is within the LM35 manufacturer specific accuracy of 0.5 degrees Celsius. In addition, the maximum hysteresis observed was only 0.6 degrees Celsius, including that the difference between the heating and cooling measurement is very, very small. Therefore, the result of calibration process was successful and that the LM35 sensor provide accurate, stable and reliable temperature measurement. So you guys can see the red line is usually for the reference that thermometer, and the blue lines at the graph is for LM35. Okay, for the next slide is the deviation graph of LM35 sensor calibration. This slide shows the deviation of the graph LM35 sensor calibration. The graph compare the measurement error between the LM35 sensor and the reference thermometer during both the cooling and heating process. The blue lines represent the cooling process, while the red line represent the heating process. The green area represent the acceptable tolerance range of 0.5 degrees Celsius, while the red area represent value outside its allowable limit. Based on the result that we can see, the maximum deviation during the cooling process was 0.4 degrees Celsius, while the maximum deviation during the heating process was only 0.2 degrees Celsius. Most importantly, all the measurement points remain within the acceptable tolerance range of 0.5 degrees Celsius. That means none of the measurement exceed the allowable error specific to LM35 sensor. Therefore, the calibration result confirm the develop of temperature monitoring system provide accurate and consistent measurement with minimal deviation from the reference thermometer. Okay, for the next one, this is a dynamic chart, or we call it the dynamic performance test. This slide present the dynamic performance test of developed temperature monitoring system. During the experiment, the LM35 was exposed to high temperature to allow it cool naturally. The temperature was recorded every 5 seconds to evaluate the sensor respond to changing temperature. Uh, As shown in the graph, the temperature gradually decreased from 45.9 degrees Celsius to 36.7 degrees Celsius within 25 seconds. The response curve is smooth without sudden fluctuation or oscillation, indicate that the sensor has a fast response time and excellent stability. This result demonstrated that the developed system is capable of monitoring temperature change continuously and accurately in real time. Therefore, the system is suitable for laboratory application as well as basic industrial temperature monitoring. In conclusion, the calibration test, deviation analysis, and dynamic performance test demonstrated that developed temperature monitor system was successful, achieved the project objective. The LM35 provide accurate, stable, and reliable temperature measurement with low percentage error and good dynamic response. Therefore, the developed system is suitable for real-time temperature monitoring application.
Everyone, our system is perfect for controlling factor process. As you can see, mixture it has four main stress. High accuracy, it has a very small error. Rock solid stability, the temperature stay with almost zero change. Repeat response is equal to quick heat change in only 25 seconds. Low cost, it gives Bremo relevancy using very variable parts. It is fast, accurate, stable, and cheap. Finally, look at our system. We can easily upgrade our system for future. We can expand it in three simple ways. First, go where is added Wi-Fi or Bluetooth to check that on your smartphone. Second, smart planning use machine learning to fix machine before they break. To upgrade it, swap the sensor where heavy deadly ones to work in harsh environments. This is the perfect foundation for a fully automatic smart factory. Thank you.